This is chapter 5, and we're covering the reactions of alkenes and alkynes. It's a little bit of a continuation of chapter 4 at the very end, when we're looking at the reaction of 2-butene with hydrogen halide. That's like HCl or HBr. Now, let me point out before we continue too much further that I'm not covering these two chapters in the lecture, and they're not going to be covered on the quiz or on the exam. Now, the homework, which I forgot to put on this first slide, is listed throughout the chapter, but in essence, you're doing all the homework problems within those sections, all the way through problem 28. And then as I go through the slides, you'll notice, for example, let me just pop one up over here. That's where you can reference back to homework 1. Then there's homework 2 and 3 down here at the bottom if you look down here. All right, so that's where you'll find the references to the problems that we'll be doing. So from the end of chapter 4, section 4.7, we talked about the reactions with the hydrogen halide. And so if we have an H, for example, Br, right, and we're doing an addition reaction. So remember, these were electrophilic addition reactions. That what you do is you draw the structure you had before minus the double bond, and then you put the hydrogen on one side of the double bond, where the double bond was, and you put the halogen on the other side. It's called the addition because you take the H and the Br and you add it to the ends where the double bond was. So in this instance, the Br will go here and the hydrogen will go here. Now, in the example that we gave at the end of chapter 4, all the alkenes look like these. That is, this one and this one are known as symmetrical or symmetric alkenes because if you draw a dashed line through the double bond, the molecule is the same on either side of the double bond. So for example, in this last one, which is the hardest one perhaps to see, if you draw the dashed line like this, you'll notice that one side is the mirror image of the other. Whenever you have a symmetrical alkene, you don't have to worry about which end the hydrogen goes on and which side the halide goes on, because regardless of which way you do it, because it's the mirror image of a mirror image position, what you'll end up having is the same molecule as the product either way. So what I'm going to do is I'm going to go ahead and pause this and fill in the answers, and then when you restart this, what you'll have is the answers in front of you, and let's see if you can match the answers that I get. All right, well, this is probably a little more than you wrote, but I wanted to make a couple of points. So I want to go through the process with you. So here, all I did was I drew the skeleton of the molecule I had before. Now you're not going to draw it like I am here, but if it helps you to learn it, yeah, go ahead and do it. Then what I did was I took each one and I put the H and the Br on different ends. But when you're looking at a symmetric molecule, you'll notice that this molecule that the pointer is at right now is actually just the reverse of this molecule. I just flipped it over, really. So when you have a symmetrical alkene, what you end up with is the same compound, regardless of how you add it. Same thing is true with this one. Remember, I put the Br at the bottom here, but I put it at the top here. But you can see how if I just rotate this molecule around, that gives us the same compound. So you should have had one of the products on the right-hand side. It doesn't really matter which one because they're the same. Now what I wanted to do is walk you through this mechanism. This is similar to the question 1. And sometimes when you're asked to draw a mechanism, you're given both the reactants and the products. And sometimes you're not given the products and you have to figure out what the product is and then you have to draw the mechanism. But in this case, we're given the structure of the product. Now, if you remember in this mechanism, where the halide shows up in the molecule, that iodine that's right there, that's where we find the carbocation in the intermediate. So I know that when I get to this point here, there's going to be a positive charge right there at the iodine like that. Okay, so now what we're going to do is we're going to draw the mechanism in the forward direction, and we're targeting that tertiary carbon for the positive charge of the carbocation. Okay, remember we have these would be secondary carbons. That's a primary, but that's a tertiary. And knowing that designation is important into determining which is the major product. So first step, double bond breaks. It attacks the H, and then the bond breaks and the electrons go towards I. Then you end up with this as your intermediate. Now, we did a little bit of talking about intermediates and their stabilities and instabilities. We'll talk about that again in this chapter. There's a positive charge here, and the H that we just added went here. And at the same time, we made our nucleophile. Remember, the iodide becomes the nucleophile in these reactions. It picks up the negative charge. Now, you think about that again, just going back and reviewing a little bit. When this bond breaks and attaches to the hydrogen, it pulls the electrons away from this tertiary carbon to leave that carbocation. And if you remember what we talked about carbocations in general are relatively unstable. So now, that instability caused it to react quickly with the iodide, and this iodide is the nucleophile now, and the carbocation is now the electrophile. And you could take any of these electrons and do that. And then when you do that, that's what gives us our product. So that's how you go about drawing the mechanism for one of these reactions. In the reactants, the nucleophile was in the reactants, the nucleophile was this guy, and in the product, and this was the electrophile. And remember, you always start the electron arrow from the nucleophile to the electrophile. Well, what we're looking at right now is something called regioselectivity. You notice that when I was drawing this structure, or and I drew this structure, why didn't I draw this? I mean, oops, sorry, that's not what it is. It's an I here. Why isn't that the product? And this is the question that we're about to answer, and it really has to do with this carbocation and its stability. So let me explain, give you two terms. The one is regioselective. One constitutional isomer is preferred over another, and we'll talk about that. And then in a regiospecific reaction, that's when you have possibility to make two products, but you only get one, okay? Or three products and you only get one, when a specific product is the product of the reaction. Now, this is what I tell students to help them think about what regioselective and regiospecific means. Usually I'll ask in class, after they graduate, anybody know where they're going to live? And most people have an idea. A lot of people just know, oh, I want to be somewhere where the air's cleaner. It could be anywhere except California. They know things like that. So what happens is people who are regioselective, or the ones that say, well, I can live in any region, but these are the characteristics of the region. People who say, I'm going to live in San Francisco, or I'm going to live in Seattle, Washington, those guys are regio-specific. They are going to a specific place. The selective people will have a lot more choices. The specific people will only have one choice. So when you're looking at a reaction, for example, 2-butene, or 1-butene like this, and you're looking at the reaction of 1-butene, there's two possible outcomes. Let's say for the addition of HBr for both, okay? The one outcome is going to be this, and the other outcome is going to be this. Now, if you actually do this reaction, this is probably over 90% of the product. Let's just say it's 95%, and the remainder, this is 5%. This is not a regiospecific reaction because I ended up with two products. It's regioselective. Now, it could be highly regioselective, but I only ended up with a mixture of products, and I didn't end up with only one. Okay, so this is the idea of regioselective versus regiospecific. Now, what causes this to happen? And it turns out it's that carbocation stability. Now, a guy named Markovnikov, he came up with this idea that uh, hydrogen halide additions to alkenes were regioselective. And he actually came up with a rule. And his rule was this: the carbon of the double bond, kind of long, but I'm going to write it up here, that has more hydrogens I have to write underneath it. Gets the hydrogen, gets the H of HX, okay, I'll put that in parentheses, and the other end, the other carbon, gets the halogen. And I'll just say gets X, that'd just be easier, okay, of the HX. There is a saying that goes along with this that helps students remember how this happens. And the saying is, the rich get richer. And I'd like to write it like this. And if you think of hydrogen as being like money, the more money you have, the more money you get. Okay, so it kind of fits with people's impressions of how things work in the world. All right, so what does this really have to do with? It has to do with the carbocation stability. This statement right here is very important. Methyl groups, and this could actually be all alkyl groups. Alkyl groups donate negative charge that can stabilize the carbocation. So look at this tertiary carbocation. There's no hydrogens on it, but it has three R groups or three alkyl groups on it. It gets a lot of stabilization for the carbocation. Now, the carbocation is still really unstable, but even though it's really unstable, it's a lot more stable because it has alkyl groups instead of hydrogens on it. Now, in a secondary carbocation, you have a hydrogen. So what does that mean? Well, there's less electron donated to the carbocation, and so as a result, the carbocation is less stable. When you go down this line from the tertiary to the secondary to the primary to the methyl carbocation gets no stabilization from alkyl groups and happens to be the least stable. So what does this have to do with which product is formed? So to answer that question, what we're going to do is we're going to look at the reaction of isobutene with HCl. So what does it look like? We do the reaction mechanism first, and then we'll talk about the reaction coordinate diagram. So isobutene is, well, isobutene, so it's this. It's that. And you'll notice the features of isobutene in terms of structure. There's a primary carbon here, and there's a tertiary carbon right here. Remember, tertiary means it has three other carbons attached to it. Now we're going to react it with HCl, and this will be the mechanism. So in the first step of the mechanism, we attack the hydrogen, and then the electrons between the hydrogen and the chloride go to the chlorine, and then I end up with a carbocation, like this. Now, I could have also ended up with this carbocation. The next step would be to add the Cl-. Remember, Cl- is made in the formation of either of these products, and I didn't draw all the electrons on the chlorine, but it would do that. And when I do that, what I would end up with is, I'd end up with this. Again, it's the same structure that I had before, but I erased the double bond, replaced it with a single bond, and I drew the other substituents on it. Now this one will look like this. All right, and so just switching the position of where they show up. Now let's talk about the reaction coordinate diagram. And again, we covered these in a little bit of detail at the end of chapter 4. So what happens is I have my reactant, and let's put the reactant there, and then I have my product. It turns out the reactants and products are the reactant is at a higher energy than the products, and the products are both around the same energy. They're not really significantly different. Now, remember, the first thing that happens is I form the carbocation. So let's say that's the carbocation right there. This is the activation energy. That's how much energy it just takes to get it started. And then once you have the carbocation, it's in this position here, right here. Okay? So that's my positively charged carbon. And then, because the products are lower in energy, it drops down like this. And remember, this guy, carbocations are high in energy, right? Because octet rule is not satisfied. Now, this carbocation, if you remember just from the previous slide, has 3 alkyl groups on it. There's carbons on each one of these points, CH3s in fact, that are donating electron density to this positive charge. This one only has 1 alkyl substituent. This whole thing is an alkyl substituent on it. So here's the deal. The tertiary carbocation is going to be lower in energy than the primary carbocation. So if this energy, and this was actually come up with by a fairly well-known chemist named Hammond, if this energy is high, then its activation energy to get to that point will also be high. And then similarly, I'll get a little low activation energy going this way. So what is the effect of having that high activation energy? If you remember what we talked about in the last chapter, that the height of the activation energy determines how fast the product gets made. Since these products both have, if these products both have similar stability, but this one has a higher activation energy, what ends up happening is very few of the molecules can make it up through this route because they got to get over the high mountain pass. If you think about a car and traveling over a mountain, right? This is going over the foothills for the tertiary, and this is going over the Sierras. Not all the cars that drive can make it over to the Sierras. This is the primary carbocation. The tertiary route is easier, so more of the molecules can come through this route, and the result is you get almost exclusively this is the product. It's the faster route because of the low activation energy. So faster route equals more product. So this is how product distributions are actually controlled in organic chemistry. It's something called kinetics. And I mean, I'm not saying always controlled, but often controlled in organic chemistry. It's something called kinetics. The products have the same energy. Sorry, that was my timer for food. That was the product. Sorry, the products are similar in energy, but the pathways to them are very different in energy, and so the lower energy pathway produces more of the product. So here's another example. This is 2-methyl-2-butene, or buteene, and hydrogen halide is hydrochloric acid. Now, another way of saying Markovnikov's rule is That's my dog. Sorry. Another way of saying Markovnikov's rule is that if an alkene is unsymmetrical, then the hydrogen always goes to the more substituted. The halogen, sorry, always goes to the more substituted carbon. In other words, the hydrogen goes to the less substituted carbon, or to the carbon with more hydrogens. So here's a hydrogen on this carbon. There are no hydrogens on this carbon. So when you do the hydrogen halide addition, the H goes here, and the Cl goes here. And that gives us our product over here. Okay, so you get 2-chloro-2-methylbutane. So this is known, again, as Markovnikov's rules. There's a bunch of ways to say it. You can talk about carbocations, you can talk about hydrogens, but they all mean the same thing. The halogen goes to where the carbocation is the most stable. So let's do a few together, and then I'll have you do B and C on your own. Predict what the products are for the hydrohalogenation reactions of these three alkenes. And then I'll go ahead and show you how we're doing it again, just to remind you. There's a double bond here, so the halogen will go here, and the hydrogen will go here. Again, this is the more substituted. So in your product, you're going to have this. And you don't have to draw this hydrogen if you don't want to, but there's hydrogen at the end. So why don't we go ahead and pause, and then I'll write out the structure for B, and then actually thinking about it, we'll go ahead and do C together, and we'll talk about what kind of product mixture you. So here's the products that you get. And again, this is the more substituted. What you do is you identify the ends of the double bond. This one's secondary, this one's tertiary. So the dominant product, the major product, will be this one where the halogen is coming off here, okay? And usually when people say, and I just realized I was doing this, when they say predict the products, they do mean what the major product is. Sometimes they'll say write all products and then predict which is the major, but it could be any combination of those. Now, if you'll notice on C, and this is why I stopped, decided we'd talk about this one. This is secondary, and this one's secondary. So they have equivalent stability as far as carbocations go. And the result is when you get your product out of this, one of your products will have the chlorine here. One of your products will have the chlorine here. And this is because, again, regioselectivity is in hydrohalogenation reactions is determined by the stability of the carbocation. These two carbocations are the same, so what you end up with is a mixture that's going to be about 50-50. Now, another kind of problem that you have to be able to do, and again, notice the homework 4 and 10, so these kinds of problems are spread out through the chapter a little bit. What alkene can be used to synthesize each of these alkyl halides? Now, when you do this problem, what you should realize is that sometimes one of the alkenes that you can draw, because most of the time you can draw two different alkenes, one of them is going to be better than the other. So, for example, for A, I know I have the bromine here, but adjacent to the bromine, I have a hydrogen could have been added there, or I could have added a hydrogen there. And what you have to do is you have to go back and you have to look at the product and then look at the reactant and then decide, like, well, will this give me more of the product I want, or will it give me a distribution of products? And so, for example, in A, there are two different alkenes that can give me that product. And remember, the only criteria is that it has to, the one end of the double bond has to be there. Now you'll notice this one's is unsymmetric, or I know I want to say asymmetric too, but the word they use is unsymmetric. They have an unsymmetric alkene. This one is symmetric. And so from symmetric alkenes, you get a single product. So that means when you do the hydrohalogenation of this reactant, even though you may not see it at first, because it's symmetric, it only gives you one product. That product will be either, well, I should say it gives you two products, but they're the same. So you're either going to get this product, or you're going to get this product. So that being the case, what you end up with is this product is exactly that product, but this is just the, if you flip it over, you'll end up with this product, right? Let's take a look at B. And for B, you're going to have maybe an alkene like that, or an alkene like this, okay? And there really are no other choices. And in this instance, right, you notice this is secondary, and that's secondary, that's secondary, and that's secondary, and it's not symmetric. So what ends up happening, so this is a secondary, right, secondary, secondary, secondary. You're going to end up with two products no matter what you do. So the only way you can get this product, product B, is in a mixture of two products that are really very similar to each other. Now, what about C? What can we do about C, right? So what I'm going to do is I'm going to pause the video and let you decide which two alkenes can give me that product, and then we'll talk about which one you choose if you had a choice. So those are the two alkenes. You notice I labeled the product that I'm looking. Oh, I labeled the product I'm looking for. That's a primary carbon. That's a tertiary carbon. That's a secondary carbon. The I is on the tertiary carbon. Now, you can get this product, right, by either this alkene on the bottom or this alkene that's at the top. Now, the alkene at the top is going to give us a better ratio because there's going to still be two products. Remember, this is regioselective and not regiospecific. So it's going to give us two products no matter what. But since a primary is so much less stable than a tertiary, rather than a secondary to a tertiary, this will give us the better product percent in the end. Here you'll get two products, but because the energies are closer together, even though the major product will be the product that you want, you'll still get more of a mixture in the second case. So before we continue on, I'd like to go over the mechanism one more time. It's very important that you get these things memorized early on because they really help you understand where the product comes from and why certain substituents are in certain places. And I hope you were able to see that in the previous slides. So what we have here is we have an alkene, this is 2-butene, and we have the hydrogen halide, in this case HCl, and we have our nucleophile, which is the electrons over here, and we have the electrophile or the electrophilic hydrogen that's right here in blue. The pi bond breaks, and again, I always like to draw a little hook if I can, but sometimes I don't. And that attacks the hydrogen. And remember, nucleophile to electrophile, and then this bond has to break because hydrogen can only accommodate one bond. Now, when you get over to the product side, this is only showing for the major product. Now that we have Markovnikov's rule, a lot of times when you do mechanisms, you're only asked to do it for the major product. We have our carbocation, which formed. Carbocation formed because the pi bond broke and attached to the hydrogen and took electrons away from this carbon. So now what we have here is this pair of electrons that makes this bond was originally this pi bond. And so it's now attached to the carbon and now the hydrogen from the hydrogen halide. This reverses the situation now. The chlorine, and I'm only showing the electrons that it received from the hydrogen, now is my nucleophile and will attack, the negative charge will attack the carbocation like this. Okay. And then just for good form, I repeated that over here. So it really only happens once. A lot of times in organic chemistry we get really lazy and we don't draw the product over again before continuing on with the arrow pushing, but this is probably a better way to do it, sort of from a teaching perspective. So you can see that both the intermediates formed in the previous reaction get used now to form our product. This pair of electrons that's shown here on the chlorine now is this bond here that's in red. And that's the mechanism, the complete mechanism for the hydrohalogenation of an alkene. Okay, so just again, by way of review, as we begin to move on to the alkyne section, in these reactions we have good electrophiles. And a good electrophile has a strong positive charge or a dipole. Another term that if you continue on with organic chemistry, you'll hear that it's polarizable. So also molecules that can have induced dipoles can also be good electrophiles. So H plus here, our hydrogen has a positive charge here. The bromine carries the negative charge. And that's generally true for all the hydrogen halides. Hi is actually polarizable, but we treat it as if it has a strong dipole because of that. HF also has a strong dipole, but it's generally not used in these reactions because it makes the reactions happen so quickly that they become violent. And finally, carbocations can actually also act as electrophiles. We do see this in some instances, but usually because carbocations are so unstable, their concentrations are low all the time. And that's why we don't see carbocations adding on to create essentially what would become polymers, long chains of the same molecule attaching to itself. So low concentrations usually keep the carbocations from acting as electrophiles in these reactions. And the other electrophile that you need to be familiar with are protonated water or alcohol molecules. So hydronium is the protonated water molecule. You can make, for example, a protonated molecule out of an alcohol too. This is the functional group for an alcohol. If you add another hydrogen onto there, remember it has a lone pair, this becomes positively charged. And that positive charge makes it so that this bond or this bond become weaker because they're able to pull away and neutralize that charge. So this is more electrophilic because the oxygen has a positive charge. The same is true for water, and if you look at the structure of water, it's a protonated water molecule, that is hydronium. It's very similar to the protonated alcohol, and that is also, they're both good electrophiles for exactly the same reason. So now what we're going to do is look at what happens when we do electrophilic reactions when water or alcohol is present as the solvent. Now, remember we just said carbocations could act as electrophiles, except for their concentrations are too low. What we're going to do in this case is we're going to create another nucleophile in the reaction by using water or alcohol as the nucleophile, as a solvent. And because it's the solvent, it'll be in high concentration, and as a result, it will act as the nucleophile instead of, let's say, a chloride ion or some other anion, which is normally the nucleophile in the reactions that you've just seen. So when water acts as a nucleophile, it'll use a lone pair, and when an alcohol acts as a nucleophile, it will also act as a nucleophile through its lone pair. Just as a big overview kind of thing, if you take an alkene and you do an electrophilic addition in the presence of water, what you end up with is an alcohol. That is, if you take this and you add water to it, and we're going to use H plus as a catalyst, what you'll end up with is an alcohol like that. And then if you do an alcohol, let's say we do this and we add an alcohol to it, and I'll do it like this, you'll end up with an ether. And this is going to be a little harder to draw, but the ether structure will look like that. The reactions still follow Markovnikov's rule. So if you're keeping track of Markovnikov's rule for this top molecule, this is less substituted, more substituted. The nucleophile, which is the water in this case, adds to the more substituted position. And here I have an alcohol, and then the alcohol, this is the secondary, this is the primary, so less substituted, more substituted. The alcohol ends up attached to the secondary carbon, again following Markovnikov's rule, and by way of that also obeying the idea that more stable carbocations are more likely to form than less stable carbocations. So what we'll do before we move on with mechanism, and you'll notice there's a bunch of problems associated with this. Before we move on with the mechanism, we'll just try to predict what we call the hydration products. You have to remember that if you have a double bond and you're adding water to it, you're actually adding an OH on one side and an H on the other. So we call these hydration reactions because the net is that you're adding H2O to the molecule. So for A, what we'll do is just like we did before, draw the skeleton of the molecule and then attach, instead of H and Br, we're going to do H and OH as the electrophile and the nucleophile in this reaction. And so for this one, where the double bond was, we can put two bonds and we can add the H to the less substituted side and the OH to the more substituted side, like that. So this is what I'd like you to do. Take a quick pause of the video and try to predict what the products for the next two are. So I've drawn most of the structure, so we can just fill it in. For B, we have tertiary versus secondary. So the expectation is I'll have the hydrogen on this side, the less substituted side, and the OH on this side. So we have this and this. And on this molecule, on molecule C, right, they're both secondary. So the result is there'll be two products of about equal concentration in the end. One product will have the H here and the OH here, and the other one will have the H here and the OH here. Okay, so it's not always the case that you get a single product in these problems. You have to make considerations, like if these are both secondary, then you end up with a distribution of two products. But if you have secondary versus a tertiary, the major product will show up at with the OH on the tertiary carbon. Again, these reactions are primarily regioselective, that they give one product in preference over another. Now, if we want to do the prediction with methanol, you have to be a little bit more careful about how you do this. So we're going to go like this. Methanol can be drawn out like this. One side's going to get an H, and then the other side's going to get the OCH3. So what you're going to do is the H goes to the less substituted side, and the OCH3, which is like the alcohol, but now because the alkyl group becomes an ether, this will go to the more substituted side. So what we're going to end up doing is breaking this double bond and adding the H to the primary side and the OCH3 to the secondary side. So what I'm going to do again is I'm going to pause the video, and I'd like you to do A, B, and C. And then when I restart the video, I will show you the answers. So here are the answers. Let's go through them one by one. So for the first one, we basically talked ourselves through that. But again, draw the structure, the skeleton that you had before. Don't draw the double bond, but instead replace it with two single bonds. And on one side, on the less substituted side, you have the H, and on the more substituted, this is the secondary side, you'll have the OCH3. Again, this is the primary, and this is the secondary. Same analysis going on here. This is a secondary versus a tertiary. So the less substituted side gets the hydrogen, then the more substituted side gets the OCH3. And because these are both secondary, I get two products out of this of approximately equal concentration. And um, in one product, the OCH3 is in the middle, and in the other product, the OCH3 is on the second carbon. All right, before we get into the details of the mechanism for the electrophilic addition reaction of alcohols and water, what I wanted to do is show you one of the detailed points that happens in these mechanisms, and it happens quite a bit. So I think it's good to look at it on its own, a little bit out of context, and then I'll point out to you where it's actually going to happen in the mechanism, and then you can see it actually taking place. So remember, in electrophilic reactions, you're going to have a carbocation. So, for example, it'll be something like this, where you have positive charge on a carbon here, and then you have another alkyl group, and you know that's part of the substrate, the reactant molecule, and then you have the nucleophile, and when you have water as a nucleophile, it's going to look something like this. The step will have an electron arrow, again nucleophile, right, to the electrophile, and then what ends up happening next, and I hope you see this, the oxygen already has two bonds, and so now it's going to pick up a third bond, and because of that it's going to have a positive charge, and because the carbon's picking up a pair of electrons, it won't have the charge anymore. Before this reaction can really go on, I'm just going to call this R and this R and have it look like something like this. So in order for this reaction to proceed, you have to remember that water is a very stable molecule. So this is actually a good leaving group, and the reaction could reverse and go back this way. So before the reaction actually proceeds, what we have to do is we have to take one of these protons off to stabilize this intermediate. So this is an intermediate with a carbocation. This is an intermediate with the protonated water molecule. And then we need to remove this to get to the stable product. So now what's going to happen is usually another water molecule will come in these particular reactions, and it will pick up that extra hydrogen, and then you're going to be left with something that looks like this. And this is actually the step at which the alcohol is finally formed and is stable and will stay this way. Now, in all electrophilic addition reactions, the product is more stable than the reactant. So this overall scheme is, well, this step could reverse. It doesn't, because this is the more stable product versus the reactant, which we have something over here. So now what we're going to do is we're going to look at a specific reaction. And by that I mean we're going to have a particular molecule and do the electrophilic addition of water. So something that you have to keep in mind in these reactions, and I'm going to write just the overall reaction here. You have H2SO4, typically is the acid that's used for this, and there's water, and then the product's going to look like this, and then following Markovnikov's rule, it'll be like something that looks like that. The extra hydrogen from the water is actually sticking off on this point, but a lot of times we don't draw that. It's assumed that there's three hydrogens at this point. I'm talking about hydronium being the electrophile, or the protonated alcohol being the electrophile. So where is that coming in? And it's right here. You have water, and you have a strong acid, and these will do an acid-base reaction, H2SO4, and we'll have an acid-base reaction which produces hydronium and then hydrogen sulfate, HSO4 minus. So this, even though we're not talking about what's going on with this, is actually going to form your hydronium ion. So this becomes your electrophile in the reaction. Now, I'm going to add that to the reaction over here. I have H3O plus, and so I'm going to draw it out like this. And remember, that positive charge makes this hydrogen more electrophilic because these electrons want to pull back to this positive charge. So what's going to happen is pi bond's going to break. And you could have gone to any of the hydrogens at, oh sorry, you could have gone to any of the hydrogens at that point. I just usually pick the ones that's closest. And then this bond is going to break, and it's going to end, that pair of electrons will end up back with the water. And then we're going to form this intermediate. Now again, because this is primary and this is secondary, the carbocation wants to be on the secondary carbon. I'm going to do that, and then I'm going to have another product over here, and that product is water. Now, this is my nucleophile for my next step. So in this next step, it's going to attack at this point here. So I'm going to do this. And then this continues on like this. And this is the point at which I have an oxygen bonded to the hydrocarbon with two hydrogens on it. So now it has a positive charge. And then one of these hydrogens has to leave. And so what we're going to do, we have to remember water is our solvent here. So I'm going to put H2O in here. It's going to attack, kick those electrons back. So now, what do I have? I have the alcohol. Remember, we would call this a secondary alcohol, plus hydronium. So you notice in this reaction mechanism, I've recreated the hydronium which is needed to react with the molecule of the hydrocarbon. So in fact, this electrophilic addition, this is a catalytic reaction. So this, the catalytic, there we go, reaction, because the water, the hydronium, right, actually never gets used. And so we would say that this is acid catalyzed. So all the extra hydronium that you created in this reaction with the sulfuric acid, oops, all the, sorry, it's not doing what I want to. All the hydronium you created with this excess acid, right, is conserved in the reaction, and you don't have to keep adding more acid to it because this hydronium that you produced here is constantly being used and regenerated. Okay, so typically in a reaction like this, you're going to add about 10% of the acid to, so zero 0.1 moles of acid for every like 1 mole of reactant, and that should make it run just fine. It's catalytic. You don't need to have a whole bunch of extra. So you're probably wondering where the alkynes were, since I said before we move on to alkynes much earlier. I had just completely forgotten about the additions of water and alcohol. I'm not going to do the one for the alcohol, but if you really want me to do one later, let me know and I'll draw one up for you. But it's exactly the same as the water reaction when you add alcohol to an alkene. So now what we're going to do is talk a little bit about alkynes. And before I get too far, there's a section on properties of alkenes and alkynes. So you should probably read that, but I'll tell you the summary. So properties of alkenes and alkynes is that the props, let me go like this, props, same as alkanes. Basically, alkenes, alkynes, and alkanes all have the same properties because they don't have any intermolecular forces. They're slightly different in terms of boiling points and things like that, but they're essentially all the same. So that's pretty much all we're going to say about it. They're not soluble in polar solvents. They're not soluble in hydrogen bonding solvents, but if you take an alkene and you can easily dissolve it into an alkane solvent. So the structure of so alkynes are only different from alkenes in that they have an extra pi bond and that their hybridizations are different. And this actually will lead to some substantially different properties. Now, when we talk about alkynes, we often make a distinction between internal and terminal. This would be terminal. It's at the end of the chain, and this would be internal. It can also, that same distinction can be made for alkenes as well. Let's see. Oh yeah, so this carbon, sp, as well as that one, and this one would be sp, sp. And remember, sp hybridization, they're linear. So a lot of times when you see a loose structure drawn of an alkyne, you'll see that done. And it does look weird because you do get used to having, we'll make this one terminal. You do get used to having that zigzag in the line. In fact, if you look online, people are sort of split on whether or not you should allow that or not. Oh shoots! But the deal is the structure of the molecule is actually linear, so it is probably better to do it like that. All right, let's take another look. Again, sp hybridized. So the bond that forms the sigma bond between the two carbons is an sp-sp, and that creates a situation now where you have two underhybridized p orbitals. Those unhybridized p orbitals are indicated by these blue colors. So you have one that's here, you have one, and that's the other half of it, and you have one here, and then underneath, you can't quite see it. But that overlap creates the pi bond. And you have another one at 90 degrees. That's this one here. And again, you don't quite see that one there. But it's this overlap that creates that pi bond. When you look at where the electrons are in an alkyne, what you'll notice is this band of red. Right? This is high, remember, high electron density. So like alkenes that have high electron density because of the pi bonds, alkynes also have high electron density and are susceptible to electrophilic addition reactions. Now, one slight difference is that when you have an alkene like this, right, these are sp2 hybridized, so they're more p orbital like and a little less s orbital like, whereas these are sp, and those are a little bit more s-like than they are p-like. And it actually turns out that changes their reactivity a little bit. S orbitals, because they hold the electrons closer to the nucleus, tend to stabilize the electrons better. And so because alkynes then are more S-like in terms of their orbital characteristics, they tend to be a little less reactive than alkenes. Well, alkyne nomenclature is very similar to alkene nomenclature. Uh, Assuming you don't have an alkene present and you're just an alkyne, then what you do is you give the alkyne priority. It becomes part of the parent chain, and we name it as an alkyne. So in this instance, we have a 1, 2, 3, 4, 5, 6 carbon chain, and so this becomes 2 hex, and then we substitute the suffix yne, hexine. And then I have a substituent over here, and this is actually one of the things that people will trip up on. That substituent is 6-chloro. A lot of times what people want to do is give this priority and they want to count this as 1 and go this way like that, increasing in numbers that way, that is incorrect because this is part of the parent chain. And it has is a higher priority than the alkyl or halo groups. Now, if there's an alkene present, let's say it looks like this. I'll do triple bond here, and then C, and then C, H, and then a double bond and a CH, and then a CH3. And you notice this one, what I've done is you can count from 1, 2, 3, 4, 5, 6, or you go 1, 2, 3, 4, 5, 6, like that. And either way, either the alkene will get the number 2 or the alkyne will get the number 2. So if you have a tie, turns out you give the alkene priority, but only if there's a tie. If there's not a tie, then whichever one gets the lowest number is the one that becomes the ending part of the name, and the other one becomes a secondary functional group in the name. We'll just do a couple examples of alkyne nomenclature since you're familiar with alkene nomenclature. Again, you identify the longest chain that contains the functional group, and then you number it so that the functional group gets the lowest possible number. So in this case, we'd number this one 1, 2, 3, 4, and 5. And so you'd have a 4-methyl and then a 2-ine. So you're going to call this 4-methyl pent 2-ine or 2-pentine. The one on the right, the molecule on the right with the halogen in it, you'll notice it can count either way. You get the same number going in either direction. So then what you have to do is, that is, in other words, 1, 2, 3, or starting at this end, 1, 2, 3. So then what you do is you look at these two substituents. They're tied in terms of where they would be. They're both on the 2 spot. So what we end up doing is deciding based on which one alphabetically comes first. So chloro would come first. So that would be 2 chloro, 5 methyl, and then you would say it's a hexine. I forgot to count it out, but it's 6 carbons. So it would be either 6 hexine or hex 6-ine, and I don't really care which way you do it. I'm not going to be that picky. I actually prefer putting the number in the front, but there are situations where it makes more sense to have the number in the middle of the name. You also have to be able to draw alkynes, and the simplest thing to do is just draw the parent and then add the substituent. So 1 chloro, 1 hexine, that would be a terminal alkyne. So you'd have a CH on this end, and then a C, C, and then remember there's already 4 bonds on this, so we'd go CH2, CH2, CH2. That gets me to 4, so then, or 5, sorry, and then I'll do one more to CH3. Then what you do is you say, oh, it's going to be 1 chloro, so this is the number 1, so now I'm going to have to, and this is 2, I'm going to have to erase this hydrogen and then replace it with a chlorine group like that. So 4,4-diisopropyl 6-methyl 2-octine. So I'm going to do this as a line drawing. This is 1 and 2, 3, 4, and then you can zigzag 5, 6, 7, and 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So there's my 8 carbons. And if you're going to do line drawings, be sure you count those out because it's easy to make mistakes. Now, 4,4-diisopropyl, that'll actually be hard. Now remember, isopropyl is drawn like that, so you could cheat and make the bonds a little longer if you want. That would be something like that. And then 6-methyl, so you'd have a little CH3 going right there. That would be that structure. Okay? Again, this corresponds to some problems in your book, so go ahead and take a look at those. If you have questions, always send me messages. Okay, now what we're going to do is we're going to look at the reactions, hydrogen halide reactions of alkynes. And basically, the mechanisms are the same as the alkenes. They're just going to happen twice. So notice I have an internal alkyne. It's symmetric. So in the first step, I'm going to do the mechanism here. I have this. Actually, let me just draw the products out first, and then we'll go from there. So I have CH3, and then I have C, double bond, C, and then CH3. Now, there is evidence that when this happens, it's actually added in a fashion that's trans. That is, the hydrogen adds on one side and the chlorine adds on the other side, but we'll just leave it like that for now. And then the next addition is going to go like this. CH3, and then C, and I'll have 2 hydrogens added here, and then I'll have a single bond, and I'll have a chlorine and a chlorine like this, and a CH3. And this turns out to be the major product for this reaction. In other words, I don't end up with a chlorine on each end. You end up with the chlorines both being on the same carbon. Now, these are known as geminal halides, like Gemini the twins. So geminal, there's 2 terms, geminal, and a lot of people just call them gem, right? And vicinal. Oops, I think it's not the S in there. I didn't want to do it at first. Yeah, that's it, vicinal. And some people will just call that Vic. So gem and Vic. But geminal means they're on the same, and vicinal means they're in the same vicinity, which means they're next to each other on opposite ends of like where the double bond was. So you'll notice this product is the one that you get. That's with if you add a second equivalent of HCl. This would be HCl. Now, you still follow Markovnikov's rule. So if this is a reactant, then your first equivalent, that's the first mole of, like if you had 1 mole of the reactant, an equivalent would be 1 mole of the HCl. So it's the same number of moles. For the first equivalent, what you'll end up with is this. And then with the second equivalent, you're going to end up with this. Again, it'll come out geminal, and you'll end up having added the 2 hydrogens. Now, recognize there is a third hydrogen here. I just didn't draw it. But the 2 hydrogens from the HCl's will be together, and the 2 chlorines from the HCl will be together. And again, the product is geminal. All right. So, what is it about this reaction that causes this to happen? So let me just sort of quickly go through the reaction mechanism. But the first thing that happens is HCl, I'll just do one of these, is the electrophile. Again, it's an electrophilic addition reaction. You're going to do that, and you're going to form a vinyl carbocation. Now, vinyl carbocations are relatively unstable. Vinyl just means it's on the double bond. So I'm going to have an H over here, and then I'll have a positive charge over here, and then the chlorine will add. So again, from this reaction, just like I did for alkenes, the chlorine could add to this point here, and that gets me to this product here. Now, when the second HCl adds, it does exactly the same thing. It acts just like you're used to seeing for alkenes. It'll do that. But then the carbocation that you get is actually this one. All right. So this is going to be the product, the carbocation that you get. Like that. Again, you have 2 hydrogens here that you've added. and you have this chlorine and the carbocation next to the chlorine. It turns out the chlorine's lone pairs of electrons can help to stabilize this charge through resonance. In other words, it can distribute its negative charge in here and stabilize that positive charge. So because this carbocation is more stable than having the carbocation on this side, then you end up with this as your product. All right, so when you do acid catalyzed additions of water to alkynes, you get a different kind of product. So in fact, what you get is going to be called a ketone. And so it still follows Markovnikov's rule. And your electrophile is hydronium. So this is with H2SO4. This reaction is slow, so there's usually a catalyst, but I noticed your book doesn't mention it, so I'll just kind of leave it out. And I'm going to abbreviate this as just OH2+, so I don't have to draw it out every time. This bond breaks, and it does that. Okay, so it's going to follow Markovnikov's rule, but this is symmetric, so you get a single product, but it turns out the overall product in this reaction is this. And this is known as a ketone. Oh, shoots, did that wrong. Ketone. So this is known as the keto form. Okay, and again, it will follow Markovnikov's rule. So if you make the addition to propyne, that's what this would be, then what you'll end up with is CH3 on this end, and then you'll have a C, a double bond O, and then a CH3 like this. Again, this would be the keto form. And this is acetone, actually. That's stuff you use to clean your glassware in the lab. But it is also a ketone. You can recognize a ketone name by the ONE ending. That's the suffix that's used for ketones. Again, this would be acid catalyzed. It's very slow unless you add an acid, and then we also usually add a catalyst to this to make it go a little faster. So let's talk a little bit about what's going on in this reaction that makes it do that. Okay, so first step, we'll redraw that. I have hydronium, and then I end up with this as my intermediate. So now I'll take a water molecule, which I'll pull over here. Again, that's what you're left with here. That attacks, and you're going to end up with this. And then we're going to scratch this out. I'm just going to fill out. I need to use all these arrows. So then you have H3, CH, and then a double bond, and then a C, and then I have an OH2 plus like this. Now, this is protonated, and so what happens is there's an acid-base reaction. In fact, maybe I should just write this out like I normally would. It's like this. I was being lazy. Apologize. We're going to have that, and then we got to get rid of one of these. And so there's also, again, an acid-base reaction with a water. Again, it's acid catalyzed like that. And then you're left with this. And this is known as an enol. This is an ene, right, an alkene, and this is an alcohol, like that, an OL. So the name for that is an enol. It has both the ketone, both, oh, that's not both, both the ketone, or sorry, both the alkene and alcohol in it. Now, when you look at this, it turns out that the final product is going to be this. And this is the keto form that we had talked about before. So essentially what happens is this enol rearranges to form this keto molecule. And the reason it does this, and we're not going to actually do the mechanism, but I need you to recognize that you get an enol and then that you get a keto afterwards. The reason this does this, CO double bond is so much stronger than the CC double bond that it naturally goes to this form. And the mechanism for this is something that's a little bit beyond this class, but I want you to recognize there's an enol form and a keto form that's much more stable because the C double bond O is so much more stable. The last reactions that we're going to be talking about are called reduction reactions, and we'll be reducing the double bond to a single bond. So in a reduction reaction, what you'll find is that we'll add hydrogen to the double bond the same way we did the electrophilic reactions. The mechanism is very different, but in the electrophilic reactions, what we would have done is drawn the original structure and then add hydrogens instead of a hydrogen and a halide. That's what the reduction bond of the bond does. So we have a double bond or a triple bond. Typically what happens is you go all the way to the alkane. The way the mechanism works actually is kind of interesting. It's usually done with a metal catalyst like palladium or platinum, a precious metal. The hydrogen actually reacts with the surface first, independent of the alkene. A lot of times they'll say they're charging the metal surface. And by that what they mean is the hydrogen sits on the metal surface and then bonds to the metal atom. So it breaks the bonds between the hydrogen atoms and attaches it to the surface of the metal. And then what happens is the alkene or the alkyne comes in contact with the surface and produces an alkane, and in that process picks up hydrogens like this to form the alkane. Now, an interesting aspect of this particular reaction is the reason this is taking place, this part, is because the alkane is much more stable than the alkene. And so this is lower in energy, so this will drive this process forward, and that frees up space on the surface for absorbing more hydrogen atoms. And so the palladium acts as a catalyst, and then you're constantly in these kinds of reactions. If you're doing it, for example, in solution and you're bubbling hydrogen gas, you're constantly providing hydrogen gas to the metal surface. For both alkenes and alkynes, the outcome is the same. So if I had used acetylene with this reaction, I would have ended up with ethane. Like this. Now that process actually happens in two steps. The first process is the formation of the alkene. Commonly, the common name with this would be ethylene. The common name for this, I called it acetylene, and I realized that's a common name for that. But the stuff that people use in the welder's torches, it's the same material. And then the alkene gets reduced to the alkane. It turns out, though, that this step is a little bit slower than this step. So if you try to make this, you can't really stop it. It just continues on. The trick to making this stop and getting a double bond is to use one of two things. One is to use what's called a poisoned catalyst. Lindlar's catalyst is actually palladium, and palladium that's been basically covered in, um, I don't know, the poison is like a compound that blocks the activity of the platinum surface or palladium surface. And so you end up getting a slower reacting catalyst, and then you can stop this. And it turns out what's going to happen when you do this on an alkyne is that you're going to get a product that looks like this. It'll be cis or Z in its configuration because the hydrogen's added from the same side, because in order for this to react, it sits down on the metal surface and then the hydrogens add from the same side. This is actually known as a syn addition. Comes on from the same side. Now, another way to do that, a reduction of an alkene, is to use a sodium metal dissolved in liquid ammonia. And this is actually done at about minus 78 degrees Celsius. So it's very cold. And what you end up getting when you do it's called a solvated or dissolving metal ion reduction, you're going to end up getting this. And the product will end up being in the trans configuration. Now, the mechanism for this reaction is well beyond this class, but it's worth knowing this reaction because it gives you trans instead of cis. Now, one more thing to cover. Remember we talked about the hybridization of alkynes being sp2, and it becomes more S-like. We would say it has more S character. What that does is stabilizes negative charge on the carbon. So actually, it's possible to use a strong base like ammonia, amide, to pull this hydrogen off an alkyne. And oftentimes these alkynes are just known as acetylenes. And then you form what's called an acetylide ion, just like you have chlorine and chloride, same kind of terminology. So the nitrogen grabs this hydrogen off. Sorry. The nitrogen grabs this hydrogen off, like this, dumps the electrons onto the carbon, makes a carbanion, and then you get NH3 out of that because you pick up the hydrogen. So it's just an acid-base reaction. NH2 minus is a much stronger base than acetylide, so you can drive this reaction and form the acetylide ion. This is a very useful reagent, and it can be used in its own kind of substitution reaction. One is to form an acetylide, and then you can react it in a substitution. I'm just going to write substitution to replace the chlorine. So we've done addition reactions. Addition reactions, you add two things. In a substitution, you just replace one thing usually. And so we're going to replace the chlorine with the acetylide ion, and you can produce this. And I'm going to draw that bond out, and it's going to be C, triple bond C, H, like that. Now, if you wanted to, you can use another equivalent of amide. Sodium amide is usually the form of it, and then you can pull this off, and you can do the same thing. You can actually substitute this whole thing onto an alkyl halide. Just a side note, but it's an important one. Typically, these are primary alkyl halides. Those are the ones this kind of reaction works best with. There are a few instances maybe where it doesn't have to be that way, but that's usually how it goes. So if you wanted to make this compound, how would you make it? This falls in the category of something your book calls multi-step synthesis. And what multi-step synthesis means is you what series of reactions starting with acetylene would you use to make this compound? So it's not just one reaction, but it's a couple of reactions. Now you notice that we have the triple bond on the end like this. What you have to do in your head when you do these types of things, you have to think backwards. And when you're thinking backwards, we use this arrow uh, that's got two, it's like a wide body arrow, two lines going to the arrowhead. And this is really like a map going backwards to say what pieces do I have that make this molecule. And as you get familiar with these things, what you'll recognize is, oh, look, here's the functional group I'm familiar with. I had to add that on right there. And then you need to know your reactions well enough to say, well, if I had this, like this, I draw it out. I'm breaking it like this. Sorry, I keep wanting to draw an H there, but it's not. There, like that. So this would be, what would this be? This would be a halogen, sort of like a chloride or a bromide. And on this end, I would have to have something like that to do a substitution reaction. So this is a stable molecule on its own. So then the question is, how do you make this? Because this is not acetylene, this is acetylide. So the step before this, again, using this backwards thinking arrow, it's called a retrosynthetic arrow, that you would have to have this. And so this lays out the path, at least backwards, for how you would make this as the product. So basically, we have a product and we have a sort of a planning process to make that product, and that's what we're thinking through. Now, like when you plan a party, uh, you don't always say, well, I'm going to have this party, so I'm going to work backwards from the party. So we're all going to eat cake at the end, and then from the cake, then maybe I'll have 6 kids at the table, and well, that means I'll have to invite. You don't think that way, right? I hope you don't. What you normally do is you say, oh, we're going to have a party. We'll start with 6 kids, but we know this is how we want the party to end. And you actually work these problems from both ends. That is, the starting material in this case, it's acetylene. So you can think about, well, what are all the reactions I know with acetylene? And then you know the product, so you have to say to yourself, oh, well, this product has an acetylene in it. How did I add that to there? And you basically make the ends meet in the middle. The pathway to the middle is not always the same. So in this instance, though, what I'll do is I'll say starting with acetylene, I will add amide to it, and that will form my acetylide ion. And then I'll take my acetylide ion, and then I'll add my molecule that I thought of over here. That's your 1-chlorobutane. Until you go C, and you can do line drawings for this too, by the way. And then that will give you your product. Now, we don't stop there. This is still sort of in the design stages. You want to look at all the reagents that you used to make sure that they're going to give the product that you want. And then typically what people will do is they'll do this. They'll say, starting with, assuming that we find that this is the process that we want to do, draw a big arrow and go 1. This first step is I'm going to add NH2 minus, like that. And then your second step, you're going to add CH3CH2. That's why the arrow has to be big. CH2CH2Cl, like that. And those are the steps, the order in which you add the reagents to produce that as your product. Now, when I ask you to do these things, these are generally written questions. I actually want you to not to just do this part. I want you to show the thinking process, like starting with this, starting with this, I'm going to have this, and then to make that, I'm going to have to start with that. And then you'll work it out. So this is how I want you to show your work if I give it to you on a test. It's what you should be doing on your homework problems as well. So let's do the multi-step synthesis for this particular molecule. Yeah, it's the last slide. And again, this is the last problems that you'll be doing out of chapter 5. And a couple of things we'll have to be looking at in this product. You'll notice there's a double bond in here. That's the functional group. And on either end, I've added these things. All right, so those have to have been added on. And you'll notice this is 2 carbons. One of the things that you often do in these problems, you look at the number of carbons that you have. We just say, it's called counting carbons, and saying, well, where does acetylene fit into here, right? Because we're sorry. Again, we're starting with acetylene. And since we're starting with acetylene, right, we have to add these 2 to the ends of an acetylene. But this is a double bond, right? So now let's think backwards on how we might do this. So before this step, there must have been a triple bond somewhere. So I'm going to call this R, and then this would also be R because they're the same. So I'm going to have R, C, triple bond, C, and R like that. That's the thing that must be right before that. Now, here's the deal. You know how to do this because we just talked about it. You go back, look in your notes, and you'll see Lindlar's catalyst. This is cis. Lindlar's catalyst is used for making things that are in the cis configuration. I know I forgot. I meant to do that, but the computer wigged out on me. That's your acetylene. Now, what do you do before this step? Well, one of the things you would have had to done is you would have had to add one of the R groups. And so the thing that's built from is this. And then R will be an alkyl halide like that. And X, right, is the halide. It's chlorine, bromine. Bromine's always a good candidate. It's a very good leaving group. Iodine's okay as well. It's very fast. Anyways, so now what do? I have this. Well, to make this, right, you're probably going to have to, again, start with an acetylene like this. That's where that came from. And then, how did I do that? Right? Well, I had to do, again, do Rx. And then, oh my, and then I had this. Oh, it's an acetylide ion like this. And then to make that, right, I had to start with this. And I will tell you, these seem overwhelming at first, but here's what I'm going to tell you. Lots of the steps are done the same way. To add an alkyl group, you're generally going to follow this pathway. To form an acetylide, you're always going to use sodium amide. There's always going to be a proton removed. So once you do like 3 or 4 and you start to see the big picture, then these things become a lot easier to do. But the key is you have to really struggle through 3 or 4. Even if you don't quite understand what you're doing, go ahead and write them out like this. And then write it out in the forward direction. So that is, you're going to start with acetylene. And then you're going to form the acetylide. Don't worry about the reagents too much yet. But we're going to do this. And then we're going to add Rx to it. And go ahead and work it out in the forward direction. Basically, you're going to follow this backwards through this pathway. And write it all out. And then once you have all the steps, then you can start with the acetylene and the arrow and the 1 and that kind of stuff and write it all out that way as well. Okay, well, Do the homework. I'm sure there'll be lots of questions. This would be great for the muddiest points like, hey, how do I do this problem? How do I do that problem? I don't quite understand. And give each other feedback because that's the way you're going to learn. All right. And again, you can always message me if you have a question.